Hello, my name is Jairo Martinez.
Hello, my name is Kevin Liu,
My name is Beatrice Aragones.
and we are Team 1076, and our coach is Dr. Ornella Mattei from the Department of Mathematics at San Francisco State University. And we're going to present our problem. So for the competition, we've decided to solve for problem C. And the main points in problem C is that we want to show how effective the different approaches are to content moderation by focusing on how sharing misinformation can impact different moderation techniques. And the problem states that sharing misinformation has divided a large amount of population, at least into two groups. And we want to see how moderation techniques impact two or more groups over time. If we change our assumptions for the model, what would our results be? And the problem also states that our model should examine at least two different moderation techniques, which are censoring info and providing warning notices. For discussing the variables, we'll be using two SIR models to examine the two different moderation techniques. For our variables, let us change the first SIR model to NFST, where N equals to no warning, F equals the first warning, S equals the second warning, and T equals the third warning. For the second SIR model, let us change that to a UC model, where U equals to uncensored info and C equals to censored information. For our main assumptions for both of the SIR models, we'll be having a total population of 300 people. People will move on to the next group by communicating either in text or in person. Out of the population of the NFST, 284 will start off with 0 warnings, 10 people will start off with 1 warning, 5 people will start off with 2 warnings, and 1 person will have 3 warnings. For our NFST model, we are assuming that once the third warning has been given out, the user will not be able to access the inaccurate information. For our UC model, we are assuming that once people try to access the inaccurate information once, that information will totally be censored, so no one will be able to have access to it. And for the UC model, the 285 people will start off with having no censored information. 15 people will start off with having the misinformation censored. For our expectations of the two SIR models, the NFST model, for the derivative of N is decreasing since everyone will be leaving the first group. For the derivative F and derivative X, they're both increasing, then decreasing, since both are entering and leaving to different warning groups. And for the derivative T is increasing, since people will end up with the third warning. For the UC model, for the derivative U is decreasing, since everyone will be leaving the uncensored information group. And for the derivative C is increasing, since everyone will be in the censored information group in the end. And the total population stay constant for both cases.
So the derivation of model, we derive this model to graph and see its behavior. When adding our 4 groups, we get P, where P is our population. We also want to see how each group interacts with one another. We call this the pipeline. N of T interacts with F of T interacts with S of T interacts with T of T. Then as we can see at the very bottom, we can see our derivative equations. But we end up seeing these parameters K, B, and J. And they mean the rates at which one group interacts with one another. So our signs for dn over dt is negative because everyone leaves this group. df over dt and ds over dt, both of these are positive and negative because people are entering and leaving these two groups. dt over dt is positive because everyone is entering this group on the right hand side. On the right hand side, the UC group, we do the same thing for our UC model. We have U of t plus C of t is equal to P. And our pipeline is basically the same as interaction between the uncensored group interacting with the censored group. And as you can see at the very bottom, the derivatives, we have this A parameter. A means it's the rate at which people with no censored information communicate with people with censored information. du over dt is negative because everyone is leaving the initial group. dc over dt is positive because everyone is going to end up in this last group. So let's classify these models. For dn over dt, or all these models I should say, these are all non-linear models because all these functions are being multiplied. So for example, we have dn over dt is equal to negative k of n. This n and f are being multiplied together, therefore it is non-linear, and this applies for the rest of the functions. These are all first order differential equations because we're only deriving each equation once. These are all homogeneous equations because each derivative has their function on each term. We bolded it, which lets us move the term from the right hand side to the left hand side, making the right hand side equal to 0. Therefore, these are all homogeneous differential equations. We have our equation here equal to P. When we derive it, on the left-hand side, we have the function's derivative form, and on the right-hand side, we have equal to 0. So here we use Euler's method and difference of quotients, where h is our step size. We use this because we want to find our next data point. So here's an example. We have dn over dt. Using our difference of quotients and Euler's method, all we have to do is isolate n of n plus 1 to find our next data point. We use this approach for every other differential equation that we have for our NFST model. So same thing here, same with the UC model. Here we use Euler's method, difference of quotients to find. All we have to do is isolate to find our next data point. All we have to do is isolate u of n plus 1 and c of n plus 1 to get our next data point. So here, using MATLAB, we're able to graph it, and now we have our two graphs. Now we are ready to discuss their behaviors. So starting off with NSFT graph, our assumptions are correct. Our assumptions are correct. All their values add up to 300 of a population. For example, when t is equal to 1, the sum of all four graphs will be 300, making this a valid graph. And finally, our second warning graph has a bigger hill than the first warning graph.
So when looking at the behavior of our UC graph, we can see that it matches our expectations. It follows our initial conditions that 285 people will start with uncensored information and that 15 people will start with censored information at time t equals 0. Our equation C of t is increasing as expected because it represents people moving from the uncensored info group to the censored info group. At the same time, our U of t is decreasing as expected because it is representing people leaving the initial first group. Lastly, we know that the numbers are accurate because there's an intersection point at around t equals 0.3 where the two graphs intersect at 150 people. Because they intersect, we can say that 150 plus 150 equals 300, which is our total population at that time. For our NFST model, our three parameters can greatly affect the way our model comes out. Depending on which variable out of k, b, and j is the greatest, it would affect how quickly people move on to the next group. In some situations, such as our second and third graph here, where b or j is the greatest value of 0.03, it would not allow some groups to be able to move on to the next in the pipeline because people are leaving the group too quickly for them to interact. The result will be an asymptote for either the no warning group or the first warning group. And additionally, our last group, which is our third warning group, will not be able to have a total population of 300 people at the end. In terms of our UC model, the role of parameters here determines how fast or slow the people from the uncensored information group will be moving on to the censored information group. For our first graph on the left here, we set our value of a to be equal to 0.04. This caused people to be able to move out to the other group very quickly before t equals 1. However, for our second graph on the right, we set our a value to be 0.004, which is much smaller. This caused people to move to the last group at a much slower rate, and the total population will move on to the last group after t equals 5. So what if we were to change our original assumptions for our NFST model? Let's say that after the third warning, people may go back to having no warnings at all after a certain time limit. This would result in a change in our pipeline. So because we have a change in our pipeline, we will need to add a new term in our differential equation for dn dt and dt dt. So in our equations, we added and subtracted a new term called mtn because the two groups now need to interact due to our new pipeline. For dn dt, we added the term mtn because people from dt dt are moving on to this group. At the same time, for dt dt, we are subtracting mtn because people are leaving that group. So again, what if we changed our original assumptions for the UC model? This time we would add a middle group for a pipeline. So rather than assuming that people move on from the uncensored information group to the censored information group, what if we had a group in between for half censored information? This would mean that rather than all the information being censored right away, only half the information is censored, which would result in a change in our differential equation as well as a new parameter z. So we now have new coupled terms UH and HC due to the new pipeline, where DHDT contains both terms because people are moving in and out of this group. So in conclusion, our second case, the UC model, is more effective in preventing people from coming in contact with inaccurate information better than the NFST model. This is because the moderation of misinformation spread via direct censorship is faster compared to giving our warnings before the information is censored. According to our two graphs, it would take about 5 days for the entire population to be safe from misinformation by using warnings, whereas for direct censorship, it would take less than a day for the population to be protected. So this concludes our presentation. Thank you very much.